All right, greetings Chem 116 students. Well, I want to give you a recording to fill in some things I won't dwell on during class time from the start of chapter 12. This has to do with the basic nature of organic compounds, and their simplest group is the alkanes. The intent is to get familiar to understand some general characteristics of organic molecules, particularly the tetravalent nature of carbon and how it's expressed in its compounds. In class, we will spend more time talking about functional groups and identifying functional groups in organic molecules. But let's get an introduction here. This will save us a little bit of anxiety for those who like some more time. The nature of organic molecules is the first section of this chapter, and their idea is what is it that gives you the basic properties of organic compounds. In general, I'm going to ask you to read some sections like this on your own. Read on your own is what ROYO infers, but I'm going to give you a little recording to fill some things in here now. Carbon is always going to be tetravalent. Tetravalent means 4. It has 4 bonds and only 4 bonds. In our normal context, that we're not looking for anything that doesn't have 4 bonds for carbon. If it doesn't have 4 bonds, you need to reevaluate. The simplest compound in organic chemistry with carbon and 4 bonds is 1 carbon and 4 bonds to hydrogens, and that is methane, also known as natural gas. Very simple looking structure with a formula of CH4. There is more than one way to do this, but with 4 bonds and more carbons, but we'll look at them gradually. So the one thing that you want to remember for the day and from this particular conversation is that carbon has 4 bonds, only 4 bonds, and that's your take-home lesson for this particular discussion. So it can occur as 4 single bonds, such as shown with methane here. You can have single and double bonds together in the same compound, or you could have single and triple bonds, and who knows, all kinds of possible combinations. But as long as there's 4 bonds on carbon, those are ordinary structures and the way we expect to see them. A few other characteristics of covalent molecules for organic compounds are worth a few comments, although this is strictly nothing more than in your textbook. Organic molecules have the kind we'll be studying in general covalent bonds. That means shared pairs of electrons hold them together. This means not ionic bonds, and so the electrons are shared rather than taken. The next example of a simple organic molecule has 2 carbons connected to one another, and since they have all single bonds, in this case there's 6 hydrogens that goes with it. We call this molecule ethane. You'll get acquainted with this gradually. Another example of carbon in tetravalent arrangements and covalent bonds. Organic molecules can contain polar bonds, and polar bonds are those that where you can draw a partial minus and a partial plus because of the differences in electronegativity between the 2 atoms in the bond. And so when carbon bonds to an element that's on the far right or left of the periodic table, most often it's going to be right in our examples, that will create polar bonds. So things like chlorine or oxygen or nitrogen, those are the sorts of things that are going to show up as polar bonds most often in the context that we will run into. So here's an example of a molecule that has a polar bond. We think of the electrons being pulled towards the chlorine away from the carbon, and the result is that you have a pink or reddish or whatever color end of the molecule, and there's electron density map for the chlorine and a bluer end for the carbon end where there's electron poor. So electron rich is pink and electron poor is blue, if that looks blue to you. It's kind of a distorted looking color. Polar bonds will be there from time to time. Carbon is going to be certainly found with multiple bonds if you share more than 2 electrons. Sharing 1 pair gives you a single bond, but if you share 2 pairs, then you get a double bond. So 2 pairs shared in this particular example at the lower right. Or if you share 3 pairs, if the carbon atoms share 3 pairs of electrons, then you get a triple bond. So all those possibilities are going to show up from time to time in the examples that we'll see. Covalently bonded molecules in organic molecules have particular 3D shapes, and there are certain things that you need to recognize. When it's got 4 bonds the angle is going to be 109 degrees thereabouts. That kind of angle that is associated with tetrahedral geometry, about 109 degrees, not exactly that, but close enough for our purposes. And if you have more than single bonds, in other words, double or triple bonds, the angles will be different for them. So if you're going to find carbon in organic molecules, the most common other atoms with it are going to be hydrogen, nitrogen, and oxygen most often. We're not going to end up using that much of the periodic table in this course. So if you want to refer to it, go right ahead, but there won't be too many variations beyond those atoms. When you have covalent bonds, you have properties in these molecules that are very different from inorganic molecules. So in general, covalent molecules have very different properties than ionic bonded molecules. Most often the inorganic molecules have more ionic compounds or ionic bonding in them. And so the contrasts are shown here. And so we'll think in terms of physical properties that are going to be the contrast. So boiling points and melting points. The boiling points and melting points are going to be less for the covalent molecules, lower, and we'll look at examples as we go, than inorganic compounds. Their solubility in water is going to be less than inorganic compounds in general. These are all generalizations. And that means they have lousy electrical conductivity compared to inorganic molecules. In other words, electrical conductivity requires ions. And so if there are no ions, generally there can't be any electrical conductivity. So organic molecules are lousy electrical conductors. Generally. There's exceptions to everything if you look far enough. There are comparisons for covalent and ionic compounds back in Chapter 4 of our textbook if you want to go back and refer to them. From there, the chapter moves on to functional groups, and that will be the bulk of the conversation for the first part of the chapter, and that is to understand what functional groups are. Functional groups are part of a larger molecule that give classic characteristical things for characteristic chemical behavior. It's how we understand compounds by their functional groups. We classify them and we predict certain things about them. There's a whole table of them in your textbook that you're going to get acquainted with readily, and we'll work on them with time. We'll get more comfortable. The sooner you're comfortable, the better. So what are these functional groups? How do we use them in classifying molecules? They are going to be the things that do allow us to predict names, understand the names of compounds, their properties, and their reactions. So functional groups are terribly important as we go, and you will suddenly realize, hopefully, that there is no subtlety about this. I'm going to remind you on practically every slide in the first half of the semester that functional groups are important. The first group of organic functional groups that we'll be looking at is those which have only carbon and hydrogen present. They're only in single bonds with only carbon and hydrogen, or a halogen, sorry, that could have been another possibility here, but this time it's only carbon and hydrogen, and these are the alkanes, the topic for Chapter 12, and we will work on identifying these in class later. The functional groups are shown in Table 12.1 in your textbook. I encourage you to put a bookmark, a sticky note, a paper clip, whatever works best for you, to refer to this table and keep it where you can refer to it readily. You'll need to know all the compounds from this. We will go through them chapter by chapter as we progress through the organic chemistry. All right, that's enough for this discussion here. The rest of this will be covered in class. See you then.